Good day. In this lecture video, we will be discussing ways in estimating errors of numerical solution. As you might be aware already, numerical solutions are approximations or assumptions. Thus, there must be some criterion that has to be applied in order to determine whether an estimated solution is accurate enough. In this lecture video, I will be introducing the four measures that could be used to approximate the solutions or the correctness of your solution. And it all depends on the person doing the numerical analysis. It's up to you which of these four measures of error you are gonna choose. You are gonna use rather on your implementation of the numerical methods. Okay, to completely understand how these four measures works, here are the variables that we will be using. The x sub t of s will represent the exact solution, such as that f of x sub t of s is equals to 0. So the t of x sub t of s represents the true answer, and the x sub n of s will represent the numerically approximated solution, such as f of x sub n of s is equal to epsilon, where epsilon is close to 0. So if x sub t of s is the true solution, that means this is the exact answer. X sub ns is the approximated answer. Okay, so let's start with the four measures. Ah, okay, so here are the four measures of error. Okay, the first measure is the true error. The true error is the difference between the true solution x sub ts and the numerical solution x sub ns. So basically, this is just the difference between the two solutions that we have. Unfortunately, true error cannot be calculated since obviously the true solution is unknown, but we want other error method to be as close as a true error. So, in other words, true error cannot be computed since x sub t of s is again, it is unknown. We don't know the true solution. That's why we are using numerical solution in the first place. We are gonna assume for the true solution. So, since the true solution is not given or is unknown, we cannot compute the true error. However, we must make sure that on the other measures of error, uh, their answer or their error value should be as close as the true error. Okay, the second measure is the tolerance in f of x. So this is its formula. That is the function of x sub t of s minus the function of x sub n of s is equals to this 0 minus epsilon, or the absolute value of epsilon. So tolerance is basically the maximum amount by which a true solution can deviate from an approximate numerical solution. In this measure, the tolerance or deviation of x sub n of s from x sub ts is identified. Since since the function of x sub ts is always 0, this is always 0 since this is the true solution, f of x sub n of s should be as close to 0 as possible. So epsilon should be as close to 0 as possible. This is to prove that x sub t of s and x sub ns are values that are very close to each other. So if this value, or if epsilon is very close to 0, that means our numerical solution is close to the true solution. Okay, the third measure is the tolerance in the solution. So this method is commonly used in measuring errors on bracketing method algorithms. So as discussed, bracketing methods enclose a true solution in the domain with interval a to b. This measure suggests that the numerical solution could be between the interval. Okay, so plus or minus this one here, the tolerance, plus or minus the tolerance is as defined as this one. So basically our x sub n of s is equals to this, and the tolerance is the error that we have, wherein this this actually is the measure of error using the bracketing method. Okay, the fourth and last measure is the relative error. This measure basically approximates the true relative error. Similar to the true error, true relative error can't be solved since the value of x sub t of s is unknown. Thus, as mentioned, this measure uses estimated relative error as an approximation. So this is the estimated relative error. As discussed, numerical methods involve iteration, and each iteration it is expected that the numerical approximation of the solution is closer to the true solution. The estimated relative error used this concept in approximating and is defined as this. Okay, here we let x n sub ns as a numerical approximation of the solution at iteration n, and x sub n minus 1 sub ns as the numerical approximation on the next iteration. So basically, relative error uses progress, no, as our iteration continues. So kada iteration ga-compute ni si estimated relative error and ga-monitor siya if this gets closer and closer to zero. That means if the error gets lesser and lesser as the iteration continues. Basically, an estimated numerical approximation gets closer to the true solution, just like what I've said. It is expected that x sub this one is smaller than this one. So this, the numerator, is expected to be smaller than this one, thus effectively approximating the true relative error such as this one. Okay? So again, the true relative error, we cannot solve this since it involves the x sub t of s, which is basically unknown. But what the estimated relative error does is to approximate the true relative error here using this formula. Okay, so these are the four measures of error. So it's up to you what you're gonna use from 2, 3, and 4 in the next lecture videos where I'm gonna introduce to you some numerical methods. Okay, so that is all for the estimation of errors in numerical solution. In the next video, I'll be discussing the first numerical method named bracketing method, named bisection method. It is a bracketing method. If you have any further question, please don't hesitate to contact me, and see you on the next lecture video.